Okay, we'll get started. So lab 5, I think everyone, a lot of people have started it already. This is roughly what it will look like just as you're starting out, kind of debugging it. So the idea is you have your bright LED and yellow LED, and it is pointed directly into your photodiode. And kind of the point of this photodiode is you can kind of imagine it basically just a solar panel. And as the light shines into it, a voltage is generated. So if you notice, I'm not actually powering this LED at all. However, I'm plugging one side into ground and I'm plugging the other side into pin 2. And if we want, we can actually measure out the voltage on this. Okay, how do we measure out the voltage on the ESP32? Okay, yeah? Yeah, using the ADC that's built in that we went over just a couple days ago. Yeah. So I want to pull up that example super quick. Yeah, I think this is quite a fun lab. It's like you get to spend a lot of time with like breadboarding and stuff, and it's like wireless communication. So, okay. So as we can see, so currently we are reading in, it looks like a voltage of, I guess, 7 millivolts, 19 millivolts. I guess it kind of jumps around a little bit. And what we can do is as we shine a light onto this LED, and I guess I'm using my phone to record the audio. That's why I have a flashlight. It does. Okay, let's see. Okay, so as I go over to the LED and shine a light on it, then we see that now the voltage is different. Now, I think my photodiode is broken. I think, so with this exact same circuit, other people were having success. I was helping people in lab yesterday. Unfortunately, yeah, it does not look like it's quite working. But you can at least see that, yeah, as I shine the flashlight on it, at least the voltage changes. So you can see, yeah, I'm at like 6 millivolts, 7 millivolts. As I take this away, then now it does jump up a little bit. But I think it's actually like kind of inverted. I think as you shine light on it, the voltage is supposed to increase. And does anyone remember what numbers they got for like the voltage if you already got to this step with the photodiode? No. Yeah. Okay, well, you may see different voltages, but kind of the important part is, yeah, we can actually read out the current on this photodiode with the ADC that we showed just a couple days ago. Yeah, as I shine the light on it, then now we can change this voltage. Okay, but you may notice, right, that I guess there's a couple problems with this. One is that it's reading out very slowly. That's because I've just set it to read out the data like every kind of just 1 second. And then another thing is you can see it's like kind of jumping around. It's not very consistent. So if we wanted to make an actual serial communication protocol out of this, like a wireless serial communication protocol out of the two LEDs just kind of like facing into each other, then it's probably going to take some amount of extra effort. So, okay, let's say like maybe you have it all kind of working, and so if you remember, so the first half of the lab is just getting this yellow LED. The point is to get the yellow LED flashing to the tone of like Morse code. So if you want to send out a message, you would send out like dots and dashes according to the Morse code specification, which I think is mentioned in the lab manual. So assuming that maybe you've already done that part, maybe you asked ChatGPT to just write you a simple Python script that writes out to the Raspberry Pi GPIO, and now you have, in fact, your LED flashing like a Morse code message. The question is now, how do you write ESP code that like kind of in a safe way actually reads in that flashing data, and then we'll translate that now into the message that we are trying to send. Okay, there's honestly like a lot of engineering that goes into like wireless communication, because yeah, as signals are bouncing around the walls, or yeah, if we were using light, like just light pollution, there's just a lot of kind of error correction that we would need to implement. So, okay, let's make like a list of strategies that potentially us as the ESP designer for like the receiver of the signal, what are some strategies that we can utilize to take in the data in a fairly like error-prone way, or take in the data even if there is like error in the air? Okay, so what are some strategies? Okay, yeah.
Take some sort of average when you know you're not supposed to be generating a signal.
Say it again. I like that. Say that one more time.
Take some sort of average when you know there's not supposed to be an incoming signal.
Oh, sure. Okay. So maybe you can read kind of the ambient noise of your environment, and then maybe like find some way to kind of subtract out the ambient noise from whenever you actually are reading the signal. I actually really like that. Yeah. So maybe like calibrate to ambient noise. Okay. Fantastic. Okay. Any other ideas? Yeah.
I mean, I guess if you know, I guess like what like frequencies or wavelengths like you're supposed to mainly work with, and you might be able to at least like narrow it down to that range.
Sure. Okay. So are you kind of saying that maybe like the Raspberry Pi and the ESP should know what speeds that they can like send and receive at ahead of time?
Yeah, I think so.
Okay, and so I highly agree with that. So maybe you just say like ahead of time, maybe the Raspberry Pi like sends at a certain frequency, and then the ESP is expecting to read at that frequency. So set the, in other words, you almost imagine that that's the baud rate again. So set the baud rate ahead of time on TX and RX. Okay, good. What else can you do? Okay. Let's say we were like transmitting the data really slow. Maybe we send out like 1 dot per second. Maybe really quick, I'll pull up a Morse code diagram. Okay, so here's a diagram that I just pulled off of Wikipedia. I think this is a really great diagram that is pretty informative on how Morse code could be structured. There's no like actual official standard for Morse code, but there are like kind of just conventions. This is a common convention of Morse code. So yeah, the idea is like when we want to send out a letter, it is a combination of dots and dashes, and a dot you can think of as just like a short burst of light, and then a dash is a longer burst of light. So if I wanted to send out A, it would be like dot dash. And if I did that, if I was like shining a flashlight like on one like naval ship out like to some like naval ship, 50 miles away or something, then they would be able to read it in my signal. So that is what Morse code is generally for. It was originally for the Navy. Yeah. Okay. So you can also see that there are kind of other sort of conventions in here. So it says like the space between parts of the same letter is 1 unit. So I guess it's like the spaces between like dots and dashes is the width of a dot. And then also the space between letters is 3 units. So I guess, if I wanted to send like AA, I would first send A, then I would wait for 3 dots worth, and then I would send A again, and then wait for 3 dots worth. You can read through these. I trust your reading skills. But okay, what if now we wanted to send out maybe, like A, so we send out like really slow, we send like, dot and then dash. But maybe at the same time, like as we're sending out that data, it's like we're sending it out really slow, maybe someone like accidentally walks in front of our flashlight, like in the middle of while we're doing that. Maybe that it just causes like a tiny little blip. And what happens now if we accidentally like sample at the perfect time when someone just like kind of walks across a flashlight? Then what do? Like basically what happens if we have like dips in our signal? Yeah, so what happens is as we're sending the data, maybe we just accidentally like have little blips where maybe the data is lost for a second. Yeah.
Say you got something that was like a weird length. Say a dash is supposed to be like 2 times a dot.
Yeah, okay.
And you got something like 1.7 instead of the expected 2. You could like estimate it to be a dash instead of just a dot?
Yeah, sure. I like that. Okay, so maybe we can kind of estimate that. Maybe if the signal isn't perfect, maybe there's some sort of algorithm we can do to like adjust it to understand that it was the correct signal. Yeah. Okay, so what algorithm could we potentially do to determine whether something is like on or off at a specific unit of time? Okay. Wait, maybe strategize. So maybe chat with the person next to you. Yeah, the point is it maybe if your flashlight is maybe like sometimes it stutters or something. How do you make it so that even if you're reading in that kind of stuttery signal, you're still able to see like the overall picture? Okay, so here's my makeshift flashlight. Imagine that this is sending out a message, and then we go and we read in that message on this like photodiode. Then what we can say is maybe like we have this graph of like, voltage over time, and maybe we receive in like, I don't know, it's like 0 for a bit, and then we get maybe like, we get something, and then it goes low, and then, okay, yeah, maybe something like that. Okay, so this would be an ideal signal. This is very clearly the value like A, because this is clearly like a dot, and then this is clearly a dash. But I guess the question is, what if someone like walks in front of this flashlight right here, like right maybe at like this point or something, like maybe for just like a split second, right? It like drops down to 0. Okay, so any solutions? Yeah.
I mean, maybe the algorithm can first, I guess, like read the entire signal and then maybe like decide, I guess, you can set, I guess, like what gap lengths, I guess, are acceptable before it's considered like a different thing.
Oh, sure. Okay, so yeah, we can say like, if it suddenly drops down to like 0, maybe. So like here it drops down to 0, and then we check, well, is it like 0 for, maybe we just set like an internal time. It's like if it's 0 for the full like, I don't know, like, one microsecond or something, then that means that it is actually 0 starting here. Otherwise, like if it ends up going high before that 1 microsecond is up, then maybe that was just like a glitch or something. Sure, yeah, I like that. We could probably do something similar for when we start signal as well. We could say like if the signal has like a spike that lasts less for 1 microsecond, and we can just ignore it. Sure. Anyone else kind of think of this? Okay. Well, how would we implement this now on the ESP? So with the ESP, what's probably going to happen is we're going to be just like sampling and sampling and sampling. And maybe a naive approach is you just like sample at the same rate as like your dots. So maybe like each of these purple lines represents like one sample that you're doing. Okay. Is there a better way to do this? Is this fine? Should we sample more than this? I think we should actually, I think we should be sampling much more than this. We could probably, maybe for like every dot, maybe we actually are reading in maybe like 3 samples. So it's like 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3 or something. So there we go. So now we can probably maybe like employ some sort of like voting system or something. Or we could say like, if maybe it's only like of the 3 like samples, we check like, is it 1 for like at least 2 of them? Like if it's 1 for at least 2 of them, then that's considered a 1. If it's 0 for at least 2 of them, then that's considered a 0. And so then we can kind of clean out this signal. And like actually this signal looks pretty good, but yeah, I don't know. We could. I didn't draw it like super well, but we could potentially clean it out. Like if we had maybe like a dip, like right here. So if it suddenly like dropped, actually I'll draw it in black. So if we had a dip right here, then we would see like at this point, this like sample accidentally read a 0, but it's okay because like this sample and this sample both saw a 1. So therefore it's able to like know that was actually a 1. Yeah. This is a very common strategy across like all wireless communication, is kind of just slapping around the answer a little bit, and it's like maybe like oversampling your data a little bit so that then you can maybe go and perform, you could almost consider this as like a low pass filter. Like you're only letting in like the low frequency spikes. You're not letting in any like super like high frequency spikes. So this would, technically be considered like a low pass filter. Okay, cool. Any other strategies now? So, okay, let's say our ESP code, right, we're maybe sampling the data every second, and I'll show you the code that I currently have set up for this. Okay, so this is my current code. So all it's doing is it's just every 1 second, it is then reading out the data in the ADC. Okay, this is probably fine. And if I now want to have it run like 1,000 times faster, then I could probably just change this wait delay to just like 1 millisecond. Okay. Is this a good idea for me to just like say like, oh, delay 1 millisecond? Now this will like mean it's that I sample every millisecond. Is this going to cause us any issues? Is this going to actually give us like a consistent delay between each of our samples? No, it won't, because actually like running each of these functions could potentially take some amount of time. So maybe our delay is not going to be exactly like 1 millisecond. Another kind of just problem is, if we have maybe like multiple programs running on our ESP, then our operating system will maybe in the middle of while we're like waiting or something, maybe this program will context switch out and then start running some other completely different program. Maybe we were running some sort of other like temperature sensor or something and on like a different thread. And if we were running like 2 things at the same time, then it's very possible that by the time we are done reading the temperature sensor, we've already like missed our window for when we wanted to sample. Yeah, okay, so this is not a good strategy. And this is kind of similar to PWM, right? Like PWM was kind of a similar thing where we didn't just want to like call delay when we wanted to write to the GPIO pin. What did we do instead when we used PWM? Remember? So we had to configure like a piece of hardware inside our ESP. Technically, it was like a PWM controller, but what was inside the PWM controller that enabled us to have like very accurate, like kind of timing? Remember? Wait, okay, quickly turn to the person next to you, explain to them or ask them what the PWM controller did. Okay, anyone? How is PWM created? Okay, I will show you one more time. There wasn't a lab specifically on it, but it's very important to know. So kind of the idea with PWM is you give your PWM controller 2 parameters. And these 2 parameters, so maybe the first one would be your timer reset value. So PWM, so one thing is a timer reset value, and then the other thing is your timer threshold. Yeah, so the idea is so you might have now inside of your PWM controller, you just have a basic counter. We've all written counters before in Verilog, like you basically just have like a flip-flop that is like plugged into an adder, and then this is like plugged into like value 1, and then you have something like that, right? So this is like your counter hardware module. So imagine that this is embedded in your PWM controller. And the idea is as this counter like counts up every cycle, at some point there's going to be some reset value where we go and check, like maybe we have this reset pin right here. And like when this output is equal to this reset value, then it goes and plugs it into this reset input. So when we reach this reset value, then now the counter stops counting up. Now it resets all the way back down to 0. And then after that, then it will resume counting. And then it will continue kind of counting up like this. So this is what the timer does inside of PWM. And then you have your timer threshold, which says that anytime you are above a certain threshold, go and output like a 1 to the PWM line. So if, for example, if we wanted a 50% duty cycle, then we would say like, oh, like it's off for all of here. But now, as soon as the timer maybe reaches above this threshold, then now go and jump up to like the maximum voltage. So this red signal is like the PWM signal. Okay, so, and then the black is the counter. Okay, is this coming back at all? Okay, good. There will be a quiz question on this this weekend. Okay, PWM, good. So now imagine that maybe instead of PWM, instead all you wanted to do was just maybe use this timer. And maybe instead of having like the timer just like, you know, reset and like have whatever the GPIO pin is like setting high and low once it reaches the threshold and versus when it's below the threshold. Maybe instead you can create just a basic timer that once again, you know, you have this, yeah, this is good. So maybe you have a timer reset value still, so you know when to stop counting up. But then you also then have a callback function. Okay, so this means that now every time that the counter has reached its value, like reached its value, and this is an extremely accurate timer, this is not going to be affected by the operating system at all. Then as soon as we then reach like the timer reset value, then at this point, a callback function will be run. For example, this callback function could be like sample the sample the ADC. And I have an example of it. It is in the system. Yeah, here we go. Cool. So here is how we can use the timer on the ESP. So it's very similar to the PWM. But now instead what we do is we can specify now when we create the timer, we can specify this timer callback function. And this timer callback function, you can see all it does is it just goes and actually just prints out like function A called. So it's very simple. But if we wanted, yeah, we could instead go and say like, oh, like ADC called or something. And now if I go and run this, so I'm like, okay, cool, great. So now we can see that this function, I don't know what's happening. So this function is in fact now being run every second. I don't know why it's getting this error. It wasn't getting that error earlier, but anyways, okay. So you can see, yeah, every second it is calling this function. And if we want, instead of every second, instead we can go and set this polling rate right here. And you can see that I call this function ESP timer start periodic. Effectively what this just means is like it will rerun this timer like in a loop. So it will like count up to 1 million, I guess. It'll count up to 1 million. Then at the end, when it finally has counted up all the way up to 1 million, then it will go and run this A function. And if we want, we could now change this to now run at like 1 microsecond or something. So now every microsecond, instead, it will go and sample out the ADC or something. Most likely, our ADC won't be able to respond like fast enough for this. So maybe a good goal would maybe just be like, I don't know, you'd say like, what is that? 10 kilohertz. So you could set a goal for yourself as 10 kilohertz or something. Yeah, cool. Okay. Good. Do we have potential thoughts of how we could maybe now like sample out our LED now using this? Okay. Good. And okay, now explain to the person next to you again one more time. This will be on your quiz. So why would we want to set up a timer like this? Like, why can't we just call delay and like every say every after like 1 millisecond go and sample? Like, why is it better to use a timer? Okay, tell the person next to you. Okay, any thoughts? Yeah. So what is the purpose of this timer again? I forget. What are we doing? Use this. Yeah.
So that whenever stream context switches, it doesn't mess up the time.
Exactly. Yeah. So when our ESP context switches to a different thread that's running, maybe the operating system, the operating system is free RTOS, which is just installed when you are using ESP IDF. Anytime the operating system wants to just check in on something, maybe every millisecond, it will just context switch out and it'll run some secret operating system functionality that you need to know about. In that time, maybe we did not want the operating system to be doing that. Instead, we wanted to have full access to our ESP. And by now setting a timer, this now forces that the sample will actually happen once the timer is up. Yeah, this is generally much better. Cool. Okay. So you can get really advanced if you want. There's all sorts of different ways that you can do this lab. So you could use this timer, and this is pretty good. Another kind of built-in functionality that you can take advantage of, though, if you want, is actually the ADC, just by default, is actually already connected to a timer. And if you want, instead of creating this timer and setting this callback and then writing out the ADC value, instead what you can do is use this other example right here, this ADC continuous read. So if I open up this example, and it is kind of unwieldy, but if you're trying to go for that extra credit, then maybe I'd recommend trying to understand this example, because effectively all this does is now, instead of just reading in one single ADC value, instead what it'll do is it'll read in a bunch of ADC values spread out over some period of time. And then what you can do is read in that as an array, and then you can work off of that data and find out whether you're sending A's or B's or whatever. Okay. So I won't go too much into this because I don't want to give the extra credit away, but I think most people who did the extra credit were using this continuous read function. One person I know took advantage of I²C in some way, because some pins are actually wired differently to operate faster. So you can play around with it. Okay, the final thing that I wanted to discuss is how we actually should maybe represent the incoming data. Because if maybe we were receiving the bits, and maybe finally we figure out that okay, maybe we have received dot space dash end letter. Okay, maybe that is the message that we have successfully received. Okay, so let me go and write that out. Yeah, so maybe we have properly parsed in whatever data was being sent, but now our question is, how do we actually represent that in code? Okay, so if we were sent in the data, maybe we figured out, so it was dot and then space. I'll represent spaces with an underscore here. So dot space and then dash, and then space and then dash, and then I'll say end with an E. Okay, so let's say we've just received this data. Okay, one potential strategy we could do if we wanted to store this now inside of our ESP, we could probably just create a string where we just take this, and each one of these values is maybe an entire, a full kind of byte array, where this would be, I guess, 1, 2, 3, 4, 5, 6 bytes, and then probably a seventh to store the value. To store the null character at the end. Okay, this is pretty good. Now the question is, well, how do we go and decode this out into the value that this is? So let me check Wikipedia. I believe this is a letter. I guess it's not. I thought it was. Okay, that's okay. I'll just kind of change. I'll change this to the value G really quick. So this would be G. If we do dash dash dot, so here are all the different options of the letters. And yeah, so now the question is like, if we receive this data, how could we somehow go and convert that into the actual like letter that it represents? So what we could potentially do is we could just like hard code all these values. Like we could check like, is this value like dot dash? If so, then okay, that's A. Then we could go, but if not, then we can check the next value. We could be like, okay, is this dash dot dot dot? If so, then that's B. And then we could go to the next value. It's like, okay, is that dash dot dash dot? But that's very slow. Like going through all of these, this is going to be a very long kind of algorithm. Okay. Any thoughts on what a potentially faster algorithm could be? Yeah, if we we're trying to decode the like dash dot or something, all the dashes and dots into the actual like signal. Yeah.
You could interpret one is a 1 and one is a 0, and then just look up in an array.
Oh, okay, sure. So you're saying, so maybe interpret like the dots as a 1 and then dash as a 0 or something?
Yeah.
Sure. Okay. Absolutely. Okay. And then, so what would that then do for us?
You'd have an index, and then you'd have your hard-coded index that maps to a character instead of and then you just go and access the character at that index.
Yeah, absolutely. So, okay, so now this would store some sort of number. So if, yeah, I don't know, maybe we can say that every like dash and dot maybe is like 2 bits or something. So I'll go back to the iPad. So maybe instead of storing it as like a character string, instead maybe what we can say is like anytime we have maybe like a space, actually this is meant to be for here. So maybe anytime we have a dash, maybe this should be represented as like the bits 1, 0. Then anytime we have an empty space, maybe this is like 0, 0. Anytime we have a dash, again, so this is 1, 0. Anytime we have a space, 0, 0. And then a dot we can say is maybe 0, 1. And then maybe end is like 1, 1. Something. I don't know. We could do it kind of any way that we want. But then if we represent each one of these as like a bit, then all of a sudden now this gives us like an integer. And potentially now we could take this integer and somehow now use this as the index into some other like lookup table. So now we could have like kind of this huge lookup table, but actually doesn't even need to be like that big because there's not too many options for like how many integers we have. So now we can just go and take this value right here. Anyone know what this value is in decimal off the top of your head? Let's see, let's do a quick conversion. So this is 7 right here. And then this is, what is that? That's 8, but then times 16. That's, maybe it's a little bit complicated. And then this is 8 times, whatever. That's okay. So whatever, this is a fairly large number, but it's within the bounds of what the ESP can do. Yeah.
I mean, you could split the like ends up to 4, and that give you like a much smaller index. That'd get you into the realm of like 32 numbers.
Say it again?
If you had like 2 steps and you got rid of the end bit first, then you could encode the whole thing with just a 0 or a 1 for each thing, and then your lookup would be it'd be under 32, less than 32, your index that you're looking at.
Oh, I see. So are you saying? Sure, I think I understand. Yeah, but there's definitely other ways that you can imagine like this encoding. This one is, yeah, probably not the best one. You could instead imagine maybe like, yeah, there are other sorts of encodings. But now like imagine that we have this like, yeah, this super large array, and maybe now the super large array like goes all the way up to like whatever, like 2 to the 16. To like store like all of the possible values that we want. And then what we can do is just like every once in a while go and store like a value at it. So we can say like, oh, like maybe this value right here is like at this point in the array, and maybe this is like the value G. And then later on, like maybe somewhere else in the array, it's like, oh, well, this is maybe the value of like Y or something. Maybe over here, like this single value is like the value like 0. And so now we could go and create like a lookup table. We call this a lookup table. Yeah, cool. And this now will give us like O of 1 time complexity to decode all the value. Like it does kind of suck setting up this lookup table ahead of time, but I mean, you know, that's just like a couple hours or a few minutes, maybe ChatGPT can help or something. But then after that, it's O of 1 lookup. Yeah, it's really great. Okay. There are other strategies. You could probably use like, you could use like a hash table instead. Yeah, there's other ways to get like O of 1 lookup. But kind of, yeah, the ESP, if you spend too much time decoding the signals, that will definitely bound how fast you can actually like read in and handle incoming data. Yeah, so you always have to be like kind of very careful about how you write embedded code because of how slow your processor is on your embedded code. You only have maybe like a 1 megahertz clock as opposed to on like an x86 machine, maybe you have access to like a 5 gigahertz clock. So you can run orders of magnitude faster than you can on the ESP. All right, cool. Do we have ideas on how we can make some cool cool O of 1 lookup algorithms? Okay, good. Any other questions on Lab 5 or anything? Okay, yeah.
We have to do it on Pi, right?
So the Raspberry Pi should send out, it should transmit out on the LED the data, but the ESP is the thing that receives the data. Yeah, exactly. Okay, well, thank you everyone. I'll see you on Monday.